Hello everyone, I'm Dr. George Bartuska with the Florida Aviation Network. Welcome to Sky Insights. Today we're going to talk about icing protection systems. Icing is a very complex subject, and this is normally a one-day seminar, so we've broken it up into 3 sections. Last time I talked about aircraft structural icing. Today we'll talk about aircraft icing protection systems, and next time we'll talk about winter flying and icing systems icing. Now, weather or meteorology is considered the most difficult and least understood subject in the aviation training program. That's why we're here. Now, both in the NASA and AOPA materials, their byline is, quote, "There is no such thing as a little ice," unquote. And that's our real theme for today. Although we tend to think of icing as a winter phenomena, icing can occur anytime, anywhere, in any climate, during any season, during any flight, in moist atmospheric conditions like we have here in Florida, with air temperature as high as 90 degrees Fahrenheit outside air temperature. There's no such thing as a little ice. Icing encounters can be dangerous. Every icing encounter is unique and unpredictable. Different aircraft may react different to the same icing condition. Icing-caused accidents usually involved experienced pilots. Let me say it again. Icing-caused accidents usually involved experienced pilots. There's no such thing as a little ice. Now, in the airline operations, their priority is to keep that plane moving, get it de-ice, get it anti-ice, and get it rolling so we can have air traffic. In general aviation, however, you, the pilot, have complete responsibility for the go, no-go decision to fly based on your training and the best information available. We have to quote FAR 121.629, "No person may take off an aircraft when frost, ice, or snow is adhering to the wings, control surfaces, propellers, engine inlets, or other critical surfaces of the aircraft." Now, a concept developed by the Boeing aircraft company called the clean airplane concept is what we use as a reference when we're talking about the situation of icing. Airplane takeoff performance is based on clean surfaces. All the information in your pilot operating manual is based on a clean aircraft. Because if it's not aerodynamically clean, the result is reduced lift, increased drag, increased stall speed, potentially severe roll problems when you get airborne, and possible abnormal pitch characteristics. Ice can form on an aircraft leading edge surface at altitudes where the freezing starts and above. The average altitude where most icing occurs for general aviation pilots is around 10,000 feet. Water droplets in the air can be super cooled to below freezing temperature, down to minus 40 degrees without freezing, without actually turning into ice unless they're disturbed in some manner. We call these supercooled droplets, or SLDs. However, the aircraft surface disturbs these droplets, and they immediately turn to ice on impact with aircraft surfaces if the aircraft's not moving fast. If it's moving over 550 miles an hour, there's usually enough aerodynamic heating to prevent this. But for general aviation aircraft, the minute they hit that supercooled water, it's going to turn into ice on their wings. Ice can have a glazed look, we call it clear or smooth ice, or a rough look, rime ice. We have 3 main kinds of icing: clear icing, rime icing, and mixed icing. Clear icing occurs mostly in cumulus clouds. Rime icing occurs mainly in stratus clouds. And mixed icing, which is a combination of the two, can occur when there's wet snow in the clouds. Now here's an example of clear ice on the upper left, an example of rime ice on the upper right, and a combination of the two in the lower left. The way we keep it clear in our heads is clear ice is like ice cubes in your freezer, and rime ice is that fuzzy stuff on the inside of the freezer that tells you it's time to clean the freezer. defrost it. Now here's the same chart I used last time and I'll use next time. This is out of the Comet Education Program from NOAA. Notice if you're below the freezing level of, in this case in centigrade, in Celsius, if you're below 0 degrees C, there shouldn't be any icing because it isn't cold enough for ice to form. And if you're above minus 40 degrees, most of what's there is going to be crystals of ice, and you shouldn't have any icing. But in between there, and we say the average is around 10,000 feet, so 3,000 to 12,000 feet, there could be supercooled liquid that can turn into icing, or mixed phase clouds that can have both kinds of icing. Now, ice research started at the Ames Aeronautical Laboratory back in the 1930s. Research began in the 1930s, focusing on routing engine exhaust air to the wing leading edge forward of the main wing spar. With the outbreak of World War II, a need arose identified initially for the B-24 and the C-46, known to us as the DC-3. All-weather flying with advanced radios and blind flying equipment was limited only by the potential hazard of in-flight icing. The plane that initial research was done on was the Lockheed 12A. And here is a picture of Kelly Johnson and a wind tunnel test of that aircraft. Now here's another picture, a diagram of what that initial research and development situation looked like. Once again, they're ducting the exhaust from the engine down the leading edge of the plane in front of the wing spar. But the wings are made out of aluminum, and that exhaust heat was way too hot to use, so this was not a doable situation. However, look at this B-17. Look at the leading edges of the wings. They're the same color of aluminum as the rest of the wing. But in a later B-17, we notice that the leading edges are black. There's something there. That's what we're going to talk about today. Now, there's two kinds of ice removal in aircraft. There's anti-icing and de-icing. Anti-icing means we're going to be proactive and we're going to prevent it from happening in the first place. De-icing means it's already happened, we didn't have a way to be proactive, and now we're going to get rid of that ice. So anti-icing means being preemptive, turn on before the flight enters icing conditions. This includes thermal heat, prop heat, pitot heat, fuel vent heat, windshield heat, and fluid surface de-icers. On the other hand, de-icing, which we do after icing has occurred, is used when there's been significant ice buildup, or the icing that you can detect. It includes surface de-icing equipment such as boots, de-icing boots, which we're going to talk about, weeping wing systems, and heated wings. Now, the first thing that usually ices up on an aircraft is the propellers. Ice usually appears on propeller before it forms on the wing. It can be treated with chemicals from slinger rings on the prop hub or graphite electric resistance heaters attached to the leading edges of the propeller blades. Windshield anti-icers usually uses resistant heat to clear the windshield or chemical sprays while on the ground. Liquids used include ethylene glycol, propylene glycol, grade B isopropyl alcohol, urea, sodium acetate, potassium acetate, sodium formate, and chloride salts. But we need to be aware that these chemicals are often bad for the environment, so we got to be careful the way we use them. Thermal heat. Now I'm going to mention bleed air, and if you have no turbine aircraft experience, that isn't going to mean anything to you yet. So later in the presentation, I'm going to talk about what this bleed air is and what the source of it is. Now, air heated. Bleed air from an engine is used to heat the inlet cowls to keep ice from forming. Bleed air can be ducted to the wings to heat the wing surface as well. Ice can also build up within the engine, so shutoff valves need to be incorporated in the design. Usually used to protect leading edge slats and engine inlet cowls. Resistance heaters are used to prevent ice from forming on pitot tubes, stall vanes, temperature probes, and drain masts. Here is a Lockheed P-3 Orion. This happens to be one of the two Hurricane Hunters that NOAA uses. And if you look at that cutaway on the right, we're looking at the leading edge of an airplane wing. You can see there's ducting, and the ducting is providing hot bleed air to a path to allow it to flow above and below the leading edge of the plane. Now, de-icing boots. If all you've been flying is a Cessna 150 or 172 or small training aircraft, you may not ever having seen these yet, but on larger aircraft and older large aircraft, there were and are inflatable rubber boots that run along the leading edge of the wing and tail surfaces. And they're operated by air. They're pneumatically operated. When inflated, they expand, knocking ice off the wing surface. After ice has been removed, suction is applied to the boots, returning them to the original shape for normal flight, usually used on smaller planes and older large aircraft. These can be span-wise boots or they can be cord-wise de-icing tubes. Here we see an example of them, and now we're going to see them in operation. Excellent. Now I should mention, I'm going to back up, I should mention that in the 1950s, 60s, and 70s, there were some issues with de-icer boots where the directions were not to turn the boots on until you actually had ice, because the theory was if you kept them on all the time, the icing could form and bridge over the de-icer boot, so it was called bridging. But all the new de-icer boots that are in use today on modern aircraft, they've solved that problem. The boots go back far enough to deal with anything running back farther on the wing. So if you know you're going to be going into an icing condition, it's considered okay by the FAA to turn the boots on before you see any ice. Now, another way of dealing with this is what's called a weeping wing. And when you hear the word weeping, you think of somebody crying. Well, that's the speed of what the chemical comes out on the leading edge of the wing. Fluid is pumped through a mesh screen mounted on the leading edge of the wing and tail. The chemical is distributed over the wing surface, melting any ice. It can also be used on propeller blades and windshields. Another source is what we call electromagnetic coil mounted under the skin that induces strong eddy currents on the surface. If you're familiar with a loudspeaker coil of a stereo system, that loudspeaker coil moves because of an electromagnetic coil, and that's essentially what we have here. It delivers a mechanical impulse to the surface of which the ice is formed. Strongly opposing forces form between the coil and the skin. The resulting acceleration sheds ice from the surface. It can shed ice as thin as 5/100ths of an inch. Now, I want to have that little talk about bleed air. Most of the cars we drive today, unless you're driving a Wankel engine in an old Mazda, or most of the planes we fly today have reciprocating piston engines in them. And that piston in operation you can see on the right is a 4-cycle machine. Cycle number 1 is an intake, 2 is compression, 3 is power, and 4 is exhaust. And here's a review. We have number 1, we have intake, where the intake valve opens and the piston comes down and pulls in a fuel air mixture. Then both the valves close when the piston's coming up in the compression stroke. Then the spark plug fires and there's a power stroke forcing the piston down. And then the exhaust valve opens as the piston comes up to push it in the exhaust. Well, this is a gas turbine. This is a jet engine. It's doing the exact same thing, only continuously. It has intake, it has compression, it has combustion, it has exhaust. And we can show the two next to each other to understand that once again. We have intake, we have compression, we have combustion, and we have exhaust. The difference is the exhaust is turning a turbine wheel that's connected to the compressor wheel. Now, if I go back here, the compression section is where we get that bleed air that we use for all kinds of systems on the aircraft. And when we take it off the compressor, on average, it's at 700 degrees Fahrenheit, it's 700 PSI, just as some round numbers. Here's a simulation of what it would look like to be flowing through a typical gas turbine, turbojet. And here is a high bypass engine. And number 4 in here is the compressor section where we would be taking that bleed air off. Here's a layout of what the bleed air panel looks like on a 727. That lower right part of the panel is the icing controls, and the arrow on the left is a bleed air valve, and up above that is a place where it says TAI, which stands for Thermal Anti-Icing System. Now, a bleed air system uses a network of ducts, valves, and regulators to conduct medium to high pressure air, which is bled from the compressor section of the engine and or it's the APU if your plane has an auxiliary power unit, to various locations within the aircraft. There it's utilized for a number of functions, including pressurization, if your aircraft's pressurized, air conditioning, engine start, wing and engine anti-ice systems like we're talking about today, hydraulic system reservoir pressurization, boundary layer separation enhancement if you have that on your aircraft, and on some aircraft it's used to pressurize the fuel tanks. So that's a quick look at icing protection systems. Thank you for joining us. This is Dr. George Bartuska with the Florida Aviation Network. I'll see you next time for another weather topic. Now stand by for the number to get your wings credit.